All right, guys, welcome back. We're going to do a little bit of Chapter 19 today. Chapter 19 effectively is not on the AP test anymore. It's been cut with the last 25% of content. Now, that being said, I'm not going to not teach it to you because this will show up in a Chem 2 class in college, your second semester, probably your freshman year. If you're taking Chem 1 and Chem 2, if you're going any science route, you'll probably do both. And this will show up. So I'm going to teach it to you, even though it's no longer on the AP test. I'll give you some problems with it. We're going to go a little bit slower, though. There's no reason to rush through this chapter because, again, you don't have to know it by the AP test, which is officially May 14th. So, yeah, so anyways, that's kind of just a little bit of intro on this. Chapter 19 is titled Ionic Equilibria and Aqueous Systems. There's a couple things that we'll take a look at here. We're going to talk about buffers. We'll then get into things called solubility product constants. But it's really not too bad. I don't think. If you've done okay so far following all the other equilibrium problems we've set up, then I don't think this is too particularly difficult. But this first section is on buffers. So here we go. So what is a buffer? Well, it's going to be something that is resistant to pH change. So how are some substances able to withstand expected large pH changes with just a small pH change? So, for example, your blood has a very specific pH, and that even if you introduce a considerably strong acid or strong base to it, it actually takes quite a bit of work to get it to deviate from that pH. It's because your blood has a buffer system in it that keeps that blood at a particular pH, or as close to it as it possibly can. So it's a way of resisting pH change is what this is. So what is a buffer and how it works? It works on something called the common ion effect, which you'll see here. A buffer is something that lessens the impact of an external force. In this case, the external force is something trying to change the solution's pH. An acid-base buffer is a solution that lessens the impact of pH of the addition of acid or base. So add a small amount of hydronium or hydroxide to an unbuffered solution, the pH is going to go up by several units or down by several units. It changes quite a bit. Even small amounts. So if you have it unbuffered, right, just pure water, you put in a few drops of like 1 molar HCl, and all of a sudden your pH is 2. It can change very, very quickly, whereas here, it's going to not change a whole lot, okay? So we can kind of see that in this picture, what's going on here. An unbuffered solution, adding small amounts of, let's see, so on this side would be an acid. So we were originally 5 on the pH scale, but we add a little bit of acid, and all of a sudden this thing is down to 2. And on this one over here, we've added a little bit of base, and it shot up all the way to 12. So that is a significantly large change, right? You're talking several magnitudes of difference there. If this were a buffered solution, though, if we added, say, the same amount of acid to it, if it's buffered, we can prevent that crazy change and make it only 4.98. Or if we start adding base, it might only go up to 5.02 instead of making this extreme pH change, okay? So that's what we're trying to do, is we're trying to create these solutions that are buffers so that they don't have this extreme pH change by adding a little bit of acid or base to it. Okay, so that's the idea here. And it comes down to this presence of a common ion. Buffers work through what's called the common ion effect. So when you dissolve acetic acid in water, the acid dissociates slightly, right? So acetic acid, putting it in water, we get hydronium and a little bit of this acetate ion, right? Okay, we'll go ahead and label stuff underneath it here. Acetate, right? Hydronium. Okay. What happens if you now introduce acetate ions by adding a solution of the salt sodium acetate? Okay. From Le Chatelier's principle, we know that adding the acetate ion will shift the equilibrium position to the left, thus decreasing hydronium and lowering the extent of acid dissociation. So if you, say, were to put this NaCH3COO into water, well, because of that sodium, it's completely soluble. And, by the way, acetate ions are always soluble no matter what. That only is going to make sodium ions and acetate ions. Well, when you do that, if you already got a solution of this stuff here, acetic acid, and you put in sodium acetate into it, you're adding more acetate ions. And as this telling you here with Le Chatelier's principle, if I'm adding more of this stuff, this whole thing's going to shift to the left. Okay, decreasing the hydronium and lowering the extent of acid dissociation. So it's going to shift back this way, and it's not going to be quite as acidic as it was before, right? That's what it's telling you right there. Okay, the acetate ion present suppresses the acid from the dissociation as much as it does in water. The acetate ion is called the common ion because it's present in both in equilibrium. So we've got the acetate ion here from the salt, and we have the acetate ion here from the acid. Okay. Right there and right there. So the same ions, it's called the common ion effect. Okay, so you basically need either an acid or a base and a salt with the exact same ion in it. Okay, that's how you create these buffers. All right, so kind of taking a look right here. If we've got, this was my initial acetic acid concentration, and this is how much of the acetate ion was added. Notice what happens to the dissociation, right? It goes down. The more of, scroll this back up for just a sec, the more of this that I add into it, notice the less and less and less it dissociates, right? The more acetate ion I'm adding via the salt, I shift it left. Less of it dissociates, and note the pH goes up. Okay? That's the relationship here. Okay? So relative concentrations of buffer components. So it matters, this one relative to this one. What's going to create the best buffer? Okay? Right? So we'll see here, the idea is that we want to keep these concentrations as close as possible. It's going to have the least amount of effect on the change. And we're getting to that. A buffer works because the large amounts of the acidic HA and the basic anion components consume small amounts of added hydroxide or hydronium respectively. Consider what happens in a solution containing high acetic acid and high acetate ions when we add small amounts of a strong acid or, scroll down here a little bit, whoops, or base. The equilibrium expression for HA looks like this, and solving for hydronium looks like this. Okay, so just rearranging this to solve for the hydronium concentration. Well, since Ka is a constant, okay, so that doesn't really factor in. It's really this ratio to this ratio. The hydronium of the solution depends on the buffer component concentration of the acid over the ion. Okay, so notice, right, this is just a constant. So it doesn't, I mean, it does factor into the actual value, but in terms of affecting the what percentage of it is going to be hydronium, it's really this ratio here. Okay? All right. So, scroll down a little bit. Uh-oh. There we go. Okay. Well, since Ka is a constant, all right, buffer components look like this. If the ratio of HA over A goes up, then hydronium goes up. If the ratio of HA over A goes down, then hydronium goes down. Okay, and so that's what we're seeing here in these pictures underneath. Let's see if I can't just delete this thing. I don't know if I can. I can't figure out. We'll try. I'll just keep moving on. But here's what's going on in this graphic, right? So this acetate and the acetic acid, okay? If we want to, if we put some hydronium in that, notice the hydronium is going to react with this guy. Okay, it's going to add a hydrogen to this, leaving water, and we create more of this acetic acid because this hydrogen is donating to this guy. If we're going this way, okay, this hydroxide is going to react with the acid. It's going to take the H off of the acid, and we're going to create more acetate ion, and it's going to eat up some of this acetic acid. Okay, but the net change is pretty small because of how we've set this thing up. Okay, so strong acid. When we add a small amount of strong acid, the hydronium ions react with an equal amount of acetate ions from the buffer to form more acetic acid, which is what we were talking about up there. Strong base. The addition of small amounts of strong base produces the opposite result. The hydroxide ions react with an equal amount of acetic acid from the buffer to form that much more acetate ions. Okay. This time, though, the buffer component concentration ratio decreases, which decreases hydroniums. That's just going back to, right, this right here. Okay, it's just going back to what we were mentioning right up here, okay, with this bit of information, right? It's going to go down. Okay, so I want you to try these three, and this will be the last thing we do here today, but try doing A, B, and C, and input your answers. I'll give you some time to do that. Okay, so walking you through A and B, and then I'll give you a chance to do C. I want to make sure that you understand how to do this before I let you try C. But A is the easy one here. So we've got the acid dissociation equation right here. It gives us that this was initially 0.5. It gives us that this one is initially 0.5. This one doesn't matter, right? And this one starts at 0. So the change here is minus X. The hydronium is plus X. And the acetate ion is plus X. We end up with this 0.50 minus X, X, and 0.50 plus X. But we're going to treat it as X being negligible here in this particular case. So if we set up our Ka expression to look like this, remember we want a pH, so we need to solve for this guy. Rearranging for this expression gives Ka times acid concentration over ion concentration. Ka for that problem is 1.8 times 10 to the negative fifth. Both of these are 0.5, so that just simplifies to 1, which means that the hydronium concentration is the Ka and the pH is just negative log of that, so 4.74. Okay, so B, all right, says after adding base, all right, and it tells you that it's 0.020 moles of sodium hydroxide in 1 liter. So we need to make sure we get that into a molarity. I mean, it's just basically turning the moles into a molarity since the liters are 1. So my dog's making noise over there. So we end up with this 0.020 molar hydroxide ions. Well, what's that going to do? Right, this is a base. Which of these things is it going to react with? It's going to react with this particular thing, right, the acetic acid. And what it's going to do is actually remove that much of it, right? We're assuming it's all going to completely react. So if I started with, right, 0.50, okay, and I've reacted it all the way, that means now there's only 0.48 of this. But if I'm losing that much of this one, that means I'm gaining that much of this one. So I've lost this, because again, this is base reacting with the acid. So I've lost that amount to begin with. So it's no longer 0.50, it's now 0.48. But my acetate ion is now 0.52, because I've gained that because this has reacted, right? It's gone this way. And when I set this up into an ice table, I get 0.48 minus X, this one's X, and this one's 0.52 plus X. But once again, we're going to assume that X is negligible, just like we have before, okay? And we're solving for a pH, which means I'm going to go for this hydronium ion. Solving for that, right, rearranging is going to be Ka times the acid concentration over the ion concentration. And that's going to give us that this concentration is 1.66 times 10 to the negative fifth molar. And that pH is equal to the negative log of that, which is 4.78. I think your textbook says 4.77. It doesn't matter, right? It's close enough if that's what you came up with. But notice, right, adding base here didn't have a dramatic effect on the pH. Okay, they're pretty darn similar. Okay, so when you're looking at part C, okay, which says, what about adding 0.020 moles of HCl to 1 liter of the buffer solution in part A? Right, it's going to be the opposite of this, right? If I'm C, okay, I'm going to let you do it on your own. C isn't going to be 0.020 molar hydroxide ions reacting with this. C, right, is going to be 0.020 molar this guy, right, hydrogen ions, which is going to react with this. So instead of gaining that 0.02 molars, this time this side's going to be 0.048, and this one's going to be 0.52. So go ahead and try C now that you've seen these two done and see what you come up with.